continuing my chapter summaries for matter and interactions. I'm on chapter 9, collisions. There's really not too much here that we haven't already seen, but it's still pretty awesome. So let's think about the momentum principle first. So remember we have the momentum principle. It says that the net force is the change in momentum with respect to time. If that, we can write it as a change, and that's fine. You can write it as a derivative if you want. Okay, I'll do that too. dp dt. What if I want to look at the net force on a system consisting of two objects? So suppose I have a mass right here and another, I'll call that A, and one over here, I'll call that B. And I'm going to call this my system. Well, we have seen that the momentum principle works for a system. We can say F net on the system is equal to the change momentum of the center of mass of the system. And so I can calculate the center mass of that system. Remember, if we calculate the center mass, I need some coordinate system. So I could have RA, I could have RB, and then the center mass, R center of mass, would be equal to, with just these two, it's RA MA plus RB MB over MA plus MB. And you can do that for as many objects as you want. Now, if I take the derivative of this with respect to time, I take the derivative of this with respect to time, and we get the velocity of the center mass, and then is equal to the same thing, VA MA plus VB MB over MA plus MB. But if I multiply both sides by the total mass, I get the total momentum as the sum of the momentums. So the momentum of the center mass is important. And that's what would change if I have a force on the system. But what if my net force on the system, F net, is equal to 0? In that case, the change in momentum is 0. Delta P center of mass is equal to 0. Another way of writing this is to say delta P, and I'm just going to use P, is P final minus P initial equals 0, or P final equals P initial. And this is what we call conservation of momentum. And all that we need for this to be true is this. If the net force in the system is 0, then momentum is conserved. And we actually have a cheat too. Because if the collision happened over a very short amount of time, the famous example is, suppose I take a ball, and I take two balls and I throw them and they hit in the air. If I look at right before the collision and right after the collision, there is a net force, there's a gravitational force acting on them, and they're pushing on each other, right? But that's not an external force in the system. The gravitational force is, and it does change momentum. But if the collision is over such a small time interval, the change in momentum is almost 0, and so we can say that the momentum is pretty much conserved. And it's a little cheat that we have right there. But let's think about if I have 2 point masses. If I have 2 point masses that are colliding or interacting in any way, it does not have to be a collision. I can have any type of force as long as these two forces are internal force, it'd be equal and opposite forces. If I consider this my system, it's still, let's call it A plus B, A and B. Then what about the work and the F net 0 on the system? Then what's the work done on the system? It's 0. So the change in energy of the system is 0 too. Now, if these are point particles, they can only have kinetic energy. So this would be a change in kinetic energy. So the change in kinetic energy would be 0. And so I can also say the initial kinetic energy total is equal to the final kinetic energy in this particular case. And we call this an elastic collision. Now, what if I have another term in here, some delta E internal? then the sum of these has to be equal to 0 if there's no work done. But the change in kinetic energy doesn't have to be 0. Okay, so I can have a loss of kinetic energy, and that's what we call an inelastic collision. And then we have elastic, we have inelastic, and then we have perfectly inelastic. It's hard to spell. It feels like I'm taking forever writing these out, but I'm probably not. So in an inelastic collision, K initial not equal to K final. In a perfectly inelastic collision, K initial not equal to K final. And VA final equals V, that's a vector, VB final. The two things stick together. Okay, so we have three things. We have the elastic collision, kinetic energy is conserved. Inelastic, kinetic energy is not conserved. Perfectly inelastic, kinetic energy is not conserved, and they stick together. In all of those cases, though, if F net 0, momentum is conserved. And I see that people get confused with that. P initial equals P final for all three of those cases. Okay, and it has to do with the difference between we only have one kind of momentum, so the net force means the total change of momentum is 0. But if you have a more complicated system, you can have more than one type of energy, so it's not just kinetic energy. Okay, so that's that. Now, you can do these in 3 dimensions and 2 dimensions, and it is useful to think about breaking a collision into 2 dimensions. Let's think about it in 2 dimensions. So suppose I have this one, it's called particle A, and it's moving this way, and it's going to collide with particle B going that way, and then after the collision, they move on their own way or something like that. So this is A, this is B, this is A, this is B. So one of the things that we like to do is to say, if P initial equals P final, I write those as vectors. This would be P initial X, P initial Y, and then it's in the XY plane. There's no Z direction. Just for now. You could put Z if you want. It's going to be equal to P final X, P final Y, 0. Right? The vector has, if the vectors are equal, then the components have to be equal. So I can write this, I can say the initial momentum in the X direction is the final momentum in the X direction. The initial momentum in the Y direction is the final momentum in the Y direction. And these are 2 scalar equations. And that makes it a little bit more useful. And so sometimes you'll have these angles theta. Let's say this is theta A initial, theta A B initial, and this will be, let's say, theta A final, and let's say this is theta B final. I have all these angles, and they may be easy, but in general, I can write the initial X momentum is going to be mass A, velocity A initial magnitude times cosine of theta A initial. That's the X component of, if these are all measured with respect to the X-axis, plus MB VB initial cosine theta B initial equals MA VA final cosine theta A final plus MB V, that's a B, VB final cosine, this is X, these are all X's, cosine theta B final. And so some of these could be negative values, but you get a scalar equation that makes it really nice to deal with. And then you can write the same thing for the Y direction. In the Y direction, the components would have a sine theta in there if you're measuring from the X-axis. So it is sometimes useful to break these in X and Y components of momentum. You could do Z too. Okay, but normally we draw it in 2 dimensions. And if we have a collision between just 2 objects, usually we can flatten that out so we can pick the X and Y coordinates so it's in the XY plane. Now, there's a really great question about reference frames. Because suppose that I have, and I'm going to make another video about this, but suppose I have 2 things colliding. So this one's moving, and this is A, and this is B, and it's stationary. And this has some initial velocity V. Let's just call it V. And so they collide, and then afterwards, let's say they even stick together and they move off that way. And they have the same mass, this would actually be v over 2, it'd be half the speed, and that's the only way to conserve momentum. Well, what if I want to look at this in the reference frame of object A? Right, so my coordinate system is moving along like this. And in that coordinate system, the same result, it will look different, but it has to be consistent with both reference frames. So here's reference frame 1, x, y, and then here's reference frame 2, x prime, y prime, with a velocity v. So the question is, how do I make a translation? How do I represent this moving object in this new reference frame? Well, I can say the velocity v is equal to the velocity, let's call that v prime. No, that velocity is the velocity in the reference frame v prime plus the velocity of the frame, we'll call that vf. And it turns out that it does work, right? Because imagine this. In this reference frame that's stationary with respect to the background, I'm seeing this one moving, and then they collide, and then they both move away. Now imagine I'm in the reference frame of this. In that case, this one looks like it's moving towards it and collides. And so now over here, my reference frame's moving along at v, so it looks like they're moving backwards at v over 2. And kinetic energy is conserved in both cases or not, and momentum is conserved in both cases. So you can move reference frames, and in some cases, it's actually advantageous to. One of the reasons they show you is, imagine a collision between two cars. So this is going that way, and this is going that way, and they collide, and they stick together right here, and they move off with some velocity that way. If I switch to the center of frame reference, then the final momentum looks like it's not moving, right? Because now they're both stuck together, and so the final momentum 0, and it makes this collision a little bit easier to analyze, and sometimes more advantageous in more complicated situations. But let me go back to my original thing. The most important thing in this chapter is this: the 3 types of collisions. And not that you memorize what they are, but you realize that they all have conservation momentum if there's no external forces. That's the important thing. There's some other stuff in this chapter that's actually kind of cool about colliding particles of equal mass. One of the things, if they're the same mass and it's an elastic collision, then the final velocities are always perpendicular to each other. It gets pretty complicated when you're dealing with elastic collisions in 2 dimensions, because there's a lot of terms, and you have squared velocities and stuff like that. It can get messy. 1 dimension's pretty easy. Numerically, it's pretty cool. Okay, we can do complicated collisions numerically by calculating the forces between them, and I'll do another video on that. But that's where we're going to stop. Chapter 9. Nothing new here. There's really nothing new. It's stuff that we've all seen before.